Motion planning within constrained, cluttered and dynamic environments poses multiple challenges. To tackle this problem, path-parameterized control schemes have shown very attractive features. Such methods are based on a projection of the system dynamics from the Euclidean coordinate system to a moving frame attached to a parametric path, denoted as adapted frame. The resulting spatial states, progress along the path and the orthogonal distance to it, yield very appealing attributes for motion planning. To conduct this spatial reformulation, state-of-the-art methods rely on the Frenitte-Serret frame. The analytical simplifications associated to the choice of the Frenitte-Serret frame come at the expense of two disadvantages. Firstly, discontinuities arise when the curvature vanishes, causing abrupt flips in the second and third components of the frame. Secondly, it shows an unnecessary twist with respect to the frame's first component. These shortcomings lead us to the research question that we answer in this paper. Is it possible to formulate a singularity-free, continuous and twist-free spatial reformulation of the Euler coordinates, by relying on an exact and compact representation of the environment? To answer this question, our contributions are twofold. Firstly, we derive a novel spatial path parameterization applicable to any arbitrary curve without prior assumptions in its adapted frame. This results in the following statement. The motion of a three-dimensional point moving at speed v with respect to a curve parameterized by xi, with parametric speed sigma, and an adapted frame r, whose angular velocity is omega, is given by the following equations. In the paper we show that the state-of-the-art Frenitte-Serret-based reformulation is a particular case of the presented spatial parameterization. For its complete definition, the path-related functions need to be expressed in closed form. This brings us to our second contribution, where we identify the appropriateness of Pythagorean Hodograph curves to efficiently and continuously define these functions. pH curves are a subset of polynomial curves whose parametric speed is a polynomial of the path parameter. This distinctive attribute allows for computing the aforementioned parametric functions by solely depending on four polynomials. As a consequence, the parametric functions are fully defined by specifying the Bernstein coefficients of these polynomials. This implies that for a pH curve of degree 2n plus 1, all parametric functions can be encoded into 4n plus 1 coefficients. Exploiting these ingredients, we tackle the problem of motion planning in cluttered environments. Given the initial and goal positions and an occupancy map, we desire to find the optimal trajectory according to a desired criterion, such as minimum time or minimum energy. Our methodology consists on 3 steps. Firstly, we perform a convex decomposition of the free space, resulting in a set of polyhedrons. Secondly, we find a collision and twist-free pH spline by solving an optimization problem. Lastly, we combine the computed parametric curve with the derived spatial reformulation in a prediction-based controller. The resultant trajectory exploits the geometric properties of the environment when finding the optimal motion according to a desired cost function, system dynamics and input constraints. As a conclusion, the presented method shows 3 appealing properties. First, the compact parameterization of the free space into a handful of coefficients accounts for its efficiency. Second, having the environment's geometric properties embedded into the optimization eases the formulation of collision-free navigation algorithms. Third, the method's versatility is exposed by its compatibility with any prediction-based motion planner, making it applicable to any cost function and deployable in any system. As a closing remark, let's analyze how our work addresses the proposed research question. Given that our method makes no assumptions about the adapted frame, the spatial reformulation presented in the first contribution not only is singularity-free and continuous, but also shows capable to be twist-free. Moreover, by utilizing pH curves, we are able to exactly compute the parametric functions by relying solely on polynomial functions, eliminating the need for approximations. Finally, because these curves are based on a small number of coefficients, a compact representation of the environment is also achieved. For further details, check out the paper. Thanks for watching.